I said that when we turn to movement, we recognize that the basic principles of movement are preserved across the entire animal kingdom. Bodies present certain problems. Movement is more or less a single problem. It does matter whether you're moving through the air or the water or on land or through the trees, but the general manner in which this problem is addressed using bodies is relatively simple and involves physics. So bodies are physical things. They have masses and inertia, and we can begin to get a handle and understand the principles of movement when we realize that most, at least early movement, most simple movement, happens by getting various parts of the body to oscillate, to go backwards and forwards, like a pendulum or like a jellyfish undulating. And oscillators are something we know an awful lot about. We have a lot of physics, we have a lot of mathematics we can bring to bear here. So when we see an animal moving and we can describe that movement as the result of a bunch of cooperating and competing oscillators, we have the basis for doing very strong mathematical modeling. Anything that repeats periodically can be described as an oscillator. And we encounter them so frequently, and we encounter them in so many domains, that we need some jargon to deal with them. One thing that happens is if something is going through a cycle and repeating itself, we need to be able to say where it is in its cycle. Is it just starting? Is it a halfway through? Or is it nearly finished? The position within a cycle is known as phase. And there are various conventions for describing phase, unfortunately. Engineers, mathematicians, physicists all use different conventions. I like to use a number between 0 and 1. 0 being the start of a cycle, then we're a quarter of a way through a cycle at a phase of a quarter, halfway through the cycle at a phase of a half. You get the idea. And when we get back to 1, we reset to 0. Other people lean on the geometry of angles, in which 360 degrees or 2 pi radians is one cycle. So they use a number either between minus pi and pi or between 0 and 2 pi. What you're going to do, it's just mathematicians. All they're talking about is where are we in the cycle. Now, if we have two oscillators and they can interact, then they typically will exhibit some form of influence on each other, and they will become, to some extent, non-independent. They will become entrained or coupled. So two pendula, which are swinging, if they're allowed to interact even slightly, will become non-independent. Here's a nice example of it from Loughborough University. Each of these metronomes is an oscillator. There's 5 of them, and they have different, slightly different intrinsic frequencies, so they're currently independent. Now, in that example, the metronomes are in touch with each other, as it were. They influence each other through small vibrations in that board that are transmitted sitting atop the two cans. The process by which the metronomes fall into lockstep is a process of entrainment. So they get yoked together into a higher level pattern, such that each of the components works towards the pattern. You can also hear something else in that video. You can hear how each of the individual metronomes tries to fight back a little bit to assert itself. So you hear them synchronize and desynchronize and synchronize and desynchronize. Now these, of course, have no brains at all. They don't have any of the flexibility of a biological system, but they illustrate the very general form of dynamical organization we see when oscillators interact. And when they do so, we have a framework within which we can describe both the emergent collective pattern and the contribution of all the individual components. So we're working here towards a generic language that will allow us to describe basic principles of movement. And particularly when it comes to animals with limbs, there are some simple regularities that we see in all locomoting animals. Did you ever notice, for example, every animal with limbs has them in pairs, whether you're talking a millipede or a bat or a centipede or a spider, legs always come in pairs. And the two limbs that are paired are never independent of one another. They have a coupled relationship. Now, observing these kinds of regularities led to the development by an Irishman called Scott Kelso of a simple model system that can help to uncover these deep regularities. It's a model system, so it's something we can readily do experiments with. We can develop a mathematical model of, and it's been very influential. The model system in question is obtained by getting your two fingers and wagging them at the same frequency. So it's a very simple task, and the task description is really important because you can do very many things with your hands. You don't have to do this task. But when you do this task, your hands are going to become subservient to the task. You're going to wag your fingers at the same frequency. And now, before going on, stop this video and try it out for yourself and see how many ways can you wag your fingers at the same frequency. I'm not sure whether you tried that out, but what you will have found is that there are two and only two ways. This is one of the ways, and we'll call this the in-phase pattern because the fingers start their cycle at the same point, and at all times in going through their cycles, the fingers are at matched points in their cycles. So we call that in-phase. And here's the other way that you can do this. This is an anti-phase relationship where one finger is starting its cycle while the other is halfway through its cycle, and vice versa. So there's always a phase offset of a half a cycle. This is called the anti-phase pattern. Now, something rather interesting happens. If you start off in the anti-phase pattern, I'll use my whole hands now to illustrate, and you speed up, what you find is that if you don't stop it happening, you will switch to the in-phase pattern. The in-phase pattern turns out to be more stable at high speeds. The anti-phase pattern and the in-phase pattern both exist at moderate speeds, but at high speeds, only the in-phase pattern is stable. This might remind you of what happens when you walk and you speed up. You have to transition to a run. There comes a speed at which you have to transition to a run. Now, walking and running are different from this, but the general principle is still there. So in this model system, we see lots of things that are relevant to locomotion. We see at any given speed, there are multiple coordinative forms. In locomotion, we would call these gaits, like walking and trotting and galloping, but here we've got the in-phase and the anti-phase pattern. Furthermore, the availability of these forms depend on the rate, and in this particular system, at fast rates, there's only one stable form, and at slow rates, there's two stable forms. The switch from antiphase to in-phase is not matched by a switch from in-phase to antiphase. So if you start in antiphase like this, and you speed up and you end up in phase and you slow down again, there's no point at which you switch back. Shortly before the switch from one mode to the other, we find a very generic signature of reorganization in a dynamic system, and this is called critical fluctuations. That means that the system becomes much more variable. It acts as if it had more degrees of freedom just before shifting from one state to another state. You're familiar with this as well, for example, from earthquakes, where tectonic plates shift from one stable state to another stable state, and in the meantime, as they shift from one to the other, there's all kinds of variability that we experience as earthquakes. We see the same thing in the stock market. Before every stock market crash, the prices go wild. They don't just fall off a cliff and go down, they go up as well as down. So we get this increase in variability or an increase in fluctuations. prior to the shift from one stable mode of organization to another stable mode of organization. These are the sort of concepts that turn out to be very, very handy as we turn to study movement and coordination.